and you can't afford to spend that time in up to 20 hours for transatlantic flights. But if you had a bit of spare cash on you, we might just have the project for you.
Let us introduce to you the Hyperion, a hypersonic passenger transport aircraft that can carry up to 20 passengers at Mach 5 cruise over a distance of 15,000 kilometers.
My name's Chris, this is Wissam, Tony, and Min.
Hi, I'm Taryn, and this is Andrew, Barry, and Varna, who will now present to you the potential market for this aircraft.
The high costs associated with such an aircraft, we are aiming towards the high end of the wealth spectrum. Most likely, millionaires and billionaires. Now, as you can see, the majority of millionaires currently are in the USA, but there is a good portion in other areas such as China, France, Russia, and other parts of Europe. So, within these millionaires and billionaires, which specific people are likely to fly this aircraft? Well, we're considering highly specialized personnel who are expert in the field and they're very rare to find. Actors that have a very tight schedule, as Hollywood will tell you. And if there was a contender for private purchase, it would be no other than our famous Prince William Italau, who has recently purchased an Airbus A380 for $500 million. Now, this is the current market, but into the future, we expect that by 2020, the number of millionaires will increase, and that's quite a sizable market which we plan to tap into. Now, the question is, where can we fly? Well, we are restricted to fly mainly over the ocean because supersonic flight over land is currently prohibited. So, for example, you've got Sydney to San Francisco on the light blue line here, and you might be wondering why we have a right route over the land. Yes, that is true. Current supersonic flight is banned. However, in the regulations in FAR 91, it does say that you can apply to have an authorization to exceed Mach 1. And we believe that as supersonic designs are refined and methods of mitigating sonic booms are investigated, future regulations are likely to change to allow, once again, supersonic flight over land. Now, it comes to cost. As I mentioned before, only the millionaires and billionaires are likely to fly this because our estimated cost is $30.5 billion US. And we believe the majority of that will go towards research, development, testing, evaluation, and certification. Now, so it's 90% cost for that, which is not too unreasonable considering most companies do spend the majority of their initial cost on R&D. Also, no single company would be willing to take on such a risk of investing all their money. So we think that a conglomerate of companies pulling their resources, funds, and efforts together would diversify the risk of such a high risk and high return investment. So if a company was to purchase one unit, We estimate their total cost will be about $145 million for 1 year, assuming they fly the aircraft for about 1,250 hours. So that includes your fuel, navigation charges, maintenance, insurance, personnel, and depreciation. So I'd like to call Tony to present our flight profile.
Thank you, Tom. So I'm going to be talking about our sample flight profile, and this will be from Sydney to San Francisco. This is approximately 12,000 kilometers. So after taking off, we'll be doing an accelerated climb up to our cruise altitude, which is initially 21 kilometers. So in this stage, we made sure that we went supersonic outside the regulation specified limit, and we'll be cruise climbing to about 23 kilometers. This is the bulk of our trajectory, and then the engines will be shut off, and we'll be going into our glide phase. And the glide phase can be customized depending on the destination. So the reason why we're flying at such a high altitude is, well, 6 kilometers higher than the Concorde, is to maintain low drag while still having enough lift. And also, we're flying the tropopause, which offers the lowest ambient air temperature. For this sample, we're using about 18 tons, but we will be adding around 6 tons for reserve. And also, it will take about 3 hours, and the maximum horizontal G load is, well, negligible pretty much. So, I'd like to call on Wissam to talk about our configuration.
Thank you, Tony. So let's move on to our configuration of our aircraft. The configuration of our aircraft is primarily based on stability, due to the fact that the aerodynamic center moves from half a chord from subsonic to supersonic phase of the aircraft. So as you can see, the pressurized, the passenger compartment will be positioned further forward on the aircraft. And we also went for a split fuel tank design. The reason why we went for a split fuel tank design is to achieve fuel trimming. This can come to our advantage to ensure that the CG position is as close as possible to the aerodynamic center, to ensure that fuel consumption is minimized during the actual cruise flight of the aircraft. The fuel tanks will also be pressurized with nitrogen to ensure that the fuel does not vaporize at high altitudes due to the pressure difference that we encounter. Now, moving on to the actual propulsion system of the aircraft. We see many concepts coming around with the supersonic and hypersonic aircraft that they've been using hydrogen fuel propulsion systems. We considered this in our design, but unfortunately, due to the space requirements for the fuel and the actual safety issues that we encounter in the airports, this was deemed not feasible. So we went for a traditional turbojet design, which is the J58 engine, which is using the SR71. But however, it requires some slight modifications to ensure it operates at Mach 5. These slight modifications include the pre-cooler. Due to the fact that the stagnation temperature at Mach 5 is very high, we need to pre-cool the inlet temperature to ensure that our compressor and turbine blades can withstand these temperature loads. So now I'll move on to aerodynamics, which will be spoken to you about with Tara.
So the aircraft must be able to maintain aerodynamic efficiency in all phases of flight. In controlled airspaces, however, the aircraft is fly in subsonic speeds, so that will be applied to low altitude climb, approach, and of course takeoff and landing. Beyond these phases, however, the aircraft will be supersonic until it reaches a cruise at Mach 5. Here, the generation of shock waves and the effects of aerodynamic heating take place, and this is where structural considerations have to be made, as will later be discussed by Chris and Tony. So as you can see here, we applied the delta wing, compound delta wing configuration. First of all, the delta wing is known for flow separation at the leading edges, which leads to the formation of vortices at higher angles of attack, as you can see here. And we've got the strake at the front of the main wing to assist with the generation. And as for the airfoil selection, we decided to use the delta wedge airfoil to avoid the high drag low shock wave that would otherwise be caused by a conventional marker type airfoil. And this geometry was reiterated throughout the design project to accommodate for structural changes, which requires sufficient space for the wing structure. These parameters were taken from computational simulations, as we do not have access to supersonic or hypersonic testing facilities. But we did assess the subsonic characteristics of the aircraft. The maximum speed of the tunnel was run at 30 meters per second. And although this didn't actually match our design conditions for the aircraft, this allowed us to gain further understanding of the delta wing, and also we collected some data that could be used to validate our CFD methodology. So as you can see here, the tops align with the airflow at 0 degrees angle of attack. But at a high angle of attack, tops appear to flap closer to the leading edge, which implies circulation, a very low pressure region, and the presence of vortices. And as for computational simulation, we replicated this, the wind tunnel conditions for CFD to generate results and compare. As you can see here, the velocity vectors run throughout the length of the aircraft, and vortices are generated at the strake, which then are absorbed and recombined with vortices at the main wing. The velocity magnitude is represented by red, which is fast, and blue, which is slow. With correlation of the results, they were quite reasonable, so we then deemed CFD as an appropriate tool to assess the performance characteristics of the aircraft for subsonic conditions only. And from the data in this analysis, we could then design other aspects of the aircraft. Next will be Chris, who will be talking about structures.
There were three major considerations when we began our structural design. Firstly, the high thermal loads at hypersonic speeds. Secondly, the high differential pressure due to our high flying altitude and standard cabin pressure. And finally, the abnormal wing geometry. We designed our wing corresponding with the aerodynamics department so that we had a higher thickness or a more even thickness distribution all the way along the wing chord, such that we could get more structure towards the trailing edge of the wing. As you can see from this diagram, more of the structure, or more of the lift is generated towards the tip of the wing and towards the trailing edge. Because things like shrink make simplifying assumptions which did not correlate well with our wing geometry, we used the CFD. We have 20 lines across there, 100 samples along it, and using samples at each of those points multiplied by the even area, we were able to get a lift distribution 3D across our wing platform. We used this lift distribution, exported to Excel, to be able to begin to design our spars. This is our final spar configuration as well as ribs. Initially, we used other designs. We looked at them, decided on how many spars we were going to have approximately, and then started distributing them where the major wing loadings were. Finally, we had to connect it to the fuselage. We've got 4 highlighted frames there where there are rigid connections to the fuselage. These carry bending moments from the spars to the fuselage, whereas the rest of the spar connections only carry shear loads. They're evenly distributed along the fuselage to have a more even distribution of bending moments being carried into the fuselage. And now Tony will talk about fuselage design.
Thank you. So before I start, I'd just like to say, after seeing all those wonderful CATIA images, our CATIA expert Min over there, and how excellent job he's done. So back to the fuselage. We went for a semi-monocoque design throughout the entire fuselage. And like Chris mentioned, we have a very large interior and exterior pressure difference due to our flying altitude, which is higher than normal aircraft. So in the zoomed-in view there, we went for a 2-skin design with frames and stringers in between. The internal skin will be made from Kevlar composite. Which offers high tensile strength and also fatigue resistance. This will be taking all the pressure loads. And then the outer skin will be made from a combination of titanium and zirconium diboride. This is to deal with the thermo stresses. And also the fuel tanks will be made from a similar method from the Kevlar with a filament wound method. So next is Andrew, and he'll be talking about thermal management system.
Same as other supersonic aircraft, the Hyperion will be experiencing great amount of aerodynamic heating. We calculated the stagnation temperature of Mach 5 cruise speed to be 1065 degrees Celsius, and therefore we have a thermal management system on the aircraft to address this issue. So we designed to have a thermal protection layer at our leading edge, which we made up of zirconium diboride. This material has relatively high heat conductivity, so that it can associate with our fuel cooling system. This picture shows the FEA analyze of our leading edge, and we use this to determine the thickness required to keep our internal structure below 600 degrees Celsius. And we have fuel cooling pipe on this area, so we will run the fuel of the aircraft through this pipe so that we can use it as a heat sink for our aircraft. So at the very front end of the aircraft, we will have a nose sink that Taryn mentioned as well. So this nose sink can protect the frontal area from aerodynamic heating. The surface of the aircraft will be finished by iron ball paint. This paint contains carbon black material, which helps to radiate heat away from the aircraft surfaces, which also makes our aircraft color in black as well. So with the thermal management system, the Hyperion will be able to fly safely at hypersonic speed. Back to Chris for the conclusion.
Thanks very much, Andrew. We believe that this aircraft could be technologically possible in the next 10 to 20 years. As was clear from the costing stage, a large amount of money will need to be put into the research and development, particularly into materials and propulsion. This makes the costing stage a little bit speculative. We believe that this will be a high-risk project that might need to be taken on by a conglomerate of companies, but maintains a high reward. Thank you. Yes, would anyone like to ask any questions about the project? Yes?
Can you check this thing would actually rotate and take off?
Yep, so this one.
Yes, so with our actual pitching moment for the aircraft provided by the stabilizer, so that will ensure a pitching moment so it can actually rotate. The actual runway distance it's going to take is approximate, it's not final, but it will take around about 2.9 k's to rotate. And which is conforms with the actual major airports we're going to operate on.
Well, the other thing is just a comment. Closing into this case on this diagram, transport is quite difficult. So we need to think very carefully as to whether or not that is going to be a field configuration you've got.
What's the effect of the engine is extending forward? Is there any interaction at supersonic speeds due to that? I would imagine it would create some sort of compression wave. Do you see any correlation?
Yes, there will be effects. The software we've been using is best used for subsonic conditions. So we've been using Float, and I've consulted some hypersonic experts at ADVA, and they suggested that if we want to accurately model this in supersonic and hypersonic speeds, we should be using SHAP, the Supersonic Hypersonic Arbitrary Body Program, which is used by NASA and is for JAPCON. So I can't completely validate this design in supersonic and hypersonic speeds. It's a preliminary design, I suppose, but it does work for subsonic conditions.
How would the radiation effect on passengers flying so high up?
We did the initial study on the radiation, but at our altitude, the radiation levels, we calculated the radiation level and we looked at the regulation. It says that for our crew, we need to have 20 millisievert, and for passengers, we need to have 1 millisievert. have a health effect to the radiation. But our altitude and our flying time, we calculated for our crew and passengers, it is severely less than 1%, so it doesn't actually have a health effect on our passengers and crew.
What did you say the fuselage frame is made from?
So the fuselage frame, the interior skin is a Kevlar composite. The frames and the stringers is titanium. And the outer skin is a combination of zirconium diboride and titanium. So it will be more zirconium diboride in the front to deal with the heat. And as the heat is lower throughout the back, we'll be using less of it.
Where you had the double skin, did you consider the difference in performance expansion rates between all those materials?
Yep, so we haven't designed any differential joints, so expansion joints at this stage, but we do know that there's going to be differential expansion between the inner skin, the outer skin. There's also going to be differential expansion between the fuselage skin and the wing box, so there's going to have to be different joints there. And the outer wing, there's different temperature profiles as you go over the entire wing as well. We weren't able to actually get a full temperature profile from CFD, so we sort of just used panel wire, but yeah, we know that there's also going to be differential heating.
What about a way to combat water egress in the Kevlar skin? A way to combat the water egress in the Kevlar skin?
So we didn't really...
Yeah, we know that we're going to have to coat our fuel tanks definitely to avoid corrosion from the fuel directly to the Kevlar skin, but we would also have to do that with an aluminium tank, but we didn't look at water egress there.
Just going back to the fusion structure again. So you've got a Kevlar inner skin, titanium supporting things, and some other kind of outer skin. How are you going to hold it all together? I mean, what are you going to use mechanical fasteners or bonding, or what are you going to do?
Yeah, so it's perfectly bonded between all three.
Okay, so we're going to have all that bonded together, right? Now, certification authorities tend to be fairly fussy about inspectability of pressure holes, right? So we've got a bonded inner skin and a bonded outer skin. How are you going to inspect it?
While the aircraft is on the ground, we could have cutouts inside the exterior skin, so that the panels can be taken apart and we can check what's in.
Maintenance is obviously going to be a very large concern for pretty much all of our aircraft. It's one of the reasons that we're not flying all the time. We have low flight hours per year. It's another reason why we chose the grid structure. We knew that we needed to avoid acute angles, just so that we made sure that we would have easily inspectable as well.
Just wondering whether you did a rough calculation of what the ticket price would be.
We've estimated that with a ticket price of $25,000, we would generate a revenue of $208 million, which would offset the usual operating cost of $100 million that is appropriate. And considering $25,000, it is competitive with current premium services. For example, Cathay Pacific charges a peak hour from Sydney to Los Angeles about $20,000. So our main aim is that we're charging slightly higher because we are saving on time, which is the main aim of this design.
Yeah, we're looking to have this sort of presentation as a tailored range curve.
Right.
Flying across the Pacific, especially here from the US back to the EU, you encounter very strong winds, which your range is going to increase substantially. So, and then you're going to be trading tailored fuel. So it would be good to have it in there to tailored range to see it's actually commercially viable.
Does your life support system differ markedly from a normal aircraft? Life support for the passengers?
Environmental control system.
Environmental.
No, because we are having to be pressurized to same level, same cabin equivalent altitude to other aircraft, which is 8,000 feet. So
systems are required to create that environment different than what the 747?
No, because cabin will be just similar to other commercial aircraft as well, so we will just use the same system.
Your heat exchange is different.
Yeah, heat exchange and like dissipating heat will be different, but just the actual standard cabin, you'll have the same sort of standard cabin as with the normal first class.
I would like to commend you on at least trying and presenting a lot more detailed structural presentation than other groups so far.
Thank you.
I was just going to ask whether you looked at any other
So, did you use a shape, for example, to well, with the cylindrical design, it's best at taking the pressure load to make stress concentrations. And since our pressurized area is in front of the landing gear with the cutter, there's no need to make some complicated geometry to fit the landing gears under it or anything. And also our prime landing gear is also outside this area. So there's no other reason to make it a complex geometry rather than just a simple circuit.
In terms of adding stringers and those sorts of things, we did some optimization, but not a large amount, just as much as we could do.
Did you check parallel windows?
Yeah, so that's obviously something very different with our aircraft than other aircraft. The main reason we don't have windows is because of the structural considerations. We wanted to make sure the structure could actually fly. Our goal with that is to have something like a live feed directly beamed to the cabin so they don't feel suffocated or like they're just traveling in a dark box.
Did you survey Professor Page to make sure that he's not claustrophobic?
Yeah, we might get Stallion.
Looking after you like
Did you try? Did you do some sort of conceptual cabin layout?
Yeah, so that was briefly in the video.
Sorry, it looks like the seat is broken, so you'll have to sit through
Yes, we have a conceptual layout. We can talk about it while this is happening.
So it's effectively a 5 rows with 4 seats per row and separated with a in the middle. And it's pretty spacious at like 26 inches per person for the seat width, and the seat width of 30 degrees still has to. And it was kind of nice to make 8% American, so you can pretty much guarantee anyone's going to be able to.
Yep.
Where are you going to get your engines from? I know you specify the engine, but I think they've been made for.
Yeah, so propulsion's, propulsion's major thing with our Aerospace aircraft, and it's also the weakest thing in this design. So we would need to, the company that is producing it would probably need to,
like the propulsion system, like we allow for room for optimization. So you can see with like the new trends in like aircraft, which is Boeing 737, they haven't allowed room for the actual engine to be like the engine radius to be maximized. So what we're allowed for is in landing gear to ensure that new propulsion systems can come into play in this aircraft can be easily put into the aircraft without these heavy modifications.
and in terms of getting the G58, we basically need to ask the US government.
Good presentation, thanks. I'll have fun with it.
Can you make the tail ring?
Yeah, I guess like anywhere that we don't require the black paint.